Hello everyone. Today we will study the clock representation method. In this session, we mainly require everyone to master the following two aspects of knowledge. 1. Understand the definition of the clock representation method. 2. Understand the method of determining the clock representation. 1. Definition of the clock representation method. The connection of the transformer is composed of the connection method and the group number. In engineering, the group number is usually determined using the clock representation method. That is, the line electromotive force of the high voltage side is used as the minute hand of the clock. The line electromotive force of the low voltage side is used at the hour hand of the clock. In other words, the whole clock number is a group number. So, how do we use the clock representation method to determine the connection group? The determination of the group number is usually done in the phasor diagram by comparing the phase difference between the line electromotive force of the high voltage side and the line electromotive force EAB of the low voltage side. And this phase difference is an integer multiplier of 30 degrees. Then divide the phase difference by 30 to get the integer as a group number. Since the transformer operates symmetrically during normal operation, we only need to compare the line electromotive force EAB of the high voltage side with the line electromotive force EAB of the low voltage side. That's it. To facilitate comparison and match the clock method, usually in the phasor diagram, the large A is aligned with the small a, which is equivalent to the hour and minute hands of the clock running coaxially. At the same time, the phasor of the line electromotive force EAB of the high voltage side is fixed in the vertical position as the minute hand of the clock. The corresponding line electromotive force EAB of the low voltage side is used as the hour hand of the clock. Thus, based on the phase difference between them, the connection number of the three-phase transformer is obtained. To better understand, let's take the examples of Y-Y connection and Y-D connection to briefly explain how to use the phasor diagram to determine the connection. On the left, let's first observe the Y-Y connection circuit as shown in the right figure. First, we draw the phasor diagram of the high voltage side. According to the symmetry of the power supply electromotive force, the line electromotive force in the star connection circuit is 3 times the phase electromotive force. The three sides of the equilateral triangle are exactly 3 times the lines from the centroid to the three vertices. So, we first draw an equilateral triangle and find the centroid of the triangle. The lines from the centroid to each vertex are the phase electromotive forces. The three sides of the equilateral triangle are the line electromotive forces. The direction of each phase electromotive force points to the centroid. The direction of the line electromotive force follows the order of the letters, such as EAB, with the direction from point A to point B. To match the whole clock number, it is recommended to fix the line electromotive force EAB in the vertical position as the minute hand of the clock. Remember, as long as the high voltage side is a star connection, this equilateral triangle is fixed. After completing the phasor diagram of the high voltage side, draw the phasor diagram of the low voltage side. The low voltage side must draw the phasor diagram of the phase electromotive force. The two coils of the high and low voltage sides aligned up and down must be on the same core column. The two coils on the same core column must have phase electromotive forces that are either in phase or out of phase. The criteria for judgment are 1. If the starting terminals are like terminals, the phase electromotive forces on the high and low voltage sides are in phase. 2. If the starting terminals are unlike terminals, the phase electromotive forces on the high and low voltage sides are out of phase. According to the judgment criteria, by observing the like terminal signs in the Rhine diagram, it can be known that phase A on the low voltage side in diagram C is in phase with the phase electromotive force of phase A on the high voltage side. Similarly, phases B and C on the low voltage side are respectively in phase with the phase electromotive forces of phases B and C on the high voltage side. For convenience of comparison, first align the lowercase a with the capital A. Draw a parallel line to phase A through point A in the same direction. It is obvious that the phase electromotive force of phase A on the secondary side overlaps with that on the primary side. The neutral point N on the low voltage side must be on the large AN. Next, draw the phasor diagrams of phases B and C on the low voltage side. From the neutral point N, with parallel lines to the corresponding high voltage side, when joining the phasor of phase B, a parallel line to phase B on the high voltage side should be drawn through point N in the same direction. Point B must on the large AB. The same applies to phase C, as shown in the white in the figure. In short, as long as the low voltage side is a star connection, the phasor diagram of phase A should be drawn from point A. The phasor diagrams of phases B and C should be drawn from the neutral point N. After completing the phase electromotive forces on the low voltage side, connect the three vertices A, B, C from the equilateral triangle, then compare the line electromotive force of the high voltage side with the line electromotive force of the low voltage side. Divide the phase difference by 30 degrees to get the group number of the winding. It is obvious that the phase difference of this connection method is 0 degrees. So, the group number is 0, which is 12 o'clock. Next, let's look at the YD connected transformer and how to use the phasor diagram to determine the connection. Similarly, first draw the phasor diagram of the high voltage side. Since the high voltage side is also a star connection, the method of drawing the line electromotive force and phase electromotive force is the same as that of the star-star connection. Since the low voltage side is a delta connection, the phase electromotive force is equal to the line electromotive force. By observing the diagram, we can see that the corresponding relationship between the phase electromotive force and the line electromotive force is the line electromotive force EAB of the low voltage side is equal to the phase electromotive force of phase A on the low voltage side. The line electromotive force EBC of the low voltage side is equal to the phase electromotive force of phase B on the low voltage side. The line electromotive force ECA between CA on the low voltage side is equal to the phase electromotive force of phase C on the low voltage side. That is, to draw the line electromotive force, the corresponding phase electromotive force should be drawn. Similarly, to draw the phasor diagram of phase A on the low voltage side, you should find phase A on the low voltage side, and which phase on the high voltage side is on the same core column. The phase electromotive forces on the high and low voltage sides on the same core column are either in phase or out of phase. In the diagram, the starting terminals are like terminals, so the phase electromotive forces on the high and low voltage sides on the same core column are in phase. So, just draw a parallel line to phase A through point A and in the same direction. Therefore, the phase electromotive force of phase A on the low voltage side overlaps with that of phase A on the high voltage side, and the small x point, also known as point B, must be on the phase electromotive force AN on the high voltage side. After completing the phasor diagram of the phase electromotive force EB on the low voltage side, it is enough to determine the phase difference between the line electromotive force of the high voltage side and the line electromotive force of the low voltage side. Just to compare the phase difference between EAB and EAB on the low voltage side. This angle is obviously equal to 30 degrees, so the group number is 1. But at this time, it is recommended to complete the triangle. The 3 vertices of the equilateral triangle have been determined, and the 2 C points are also not difficult to determine, since the phase sequence of the power supply is usually positive. The 3 vertices of the triangle of the line electromotive force must be arranged in a clockwise direction, as shown in the white in the figure just now. We mainly introduced the definition of the clock representation method and its determination method. 2 aspects I hope you will understand and consolidate them better after class. That's all for this lesson. Thank you, everyone.